tasks. So the first task was to ask what number of neighbours gives us the best value for k-nearest neighbours algorithm. So this is one way you can actually help inform yourself how many neighbours you should be using in an algorithm. So it's very hard with k and n, just one tuning parameter, the number of neighbours. It's hard to tell straight out of the box which one you should use. And so if you use a cross-validation system, you can then inform which value of k is the best value of k for a particular data set. So what I've done here is I've gone through the k 1 to 50. You can go all, you can do more neighbours to consider as well. Focus on 1 to 50. And we can see here we do not so well. We've got too little information about from our neighbours. The lowest is at k equals 21. But if I keep on increasing the number of neighbours, I'm putting pretty much too much information and it's giving you more like a localized fit. And so it turns out 21 neighbours to consider, it just turns out to be the best value for this particular data set at the moment. Then, if I consider the random forest cross-validation loop, I haven't got the package, we get an error rate of 0. That's a bit concerning sometimes. So the random forest cross-validation rate is 24.08% straight out the bat using all, there's also defaults for random forest, but using straight out the default 24%. And the best error rate for k we never even got below that 24% using the best value of k. So in this case, random forest is doing a better job at predicting this data set, even without any tuning as it is. So there are the answers to those parts. So the one thing I want to introduce, and you can go back and work on the task more, or you can just work on to the next one. It's very similar. We're just doing more of what we were doing before. And so often what we want to do is we want to repeat this process many, many times. So you might argue, look, this, if you just do cross-validation loop, the whole thing once, it's just your error rate is dependent on those data points being those petitions or being grouped together in a certain way. And so what you want to do is you want to repeat this whole process over and over again. So you do one cross-validation loop, get an error rate, then you re-permute the data points, and then separate into folders and just over and over again. And then you get a set of cross-validation errors. And so here, this graphic was stolen from my research group's presentation. So here we've got our data set. Here's my observations. Here is my features or predictors. And I split them up into training and testing. I then, for the first cross-validation loop, I'll set it up, do a 5-fold cross-validation, and perhaps get an error rate of 33%. Then I redo it over again, and this time we're going to be different permutation of what's in testing, what's in training at the same time, and here we might get an error rate of 27%. And you do this how many times you want, how much computing power you have, or how much time you have to sit around and watch. And you do this over again, and then you get now a distribution of cross-validation errors. You get multiple repeats of the same error rate, which is good, because then you can then get a box plot of the variability associated with your prediction procedure. So this is, all you have to do is embed it in number 4 loop. So it's the same kind of process. It's not, if you've really got the k and n loop, it's not too dissimilar. So here we're going to I want to repeat this process, suppose 10 times. There's no set rule that has to be 10 times. This is an easy example, just 10 repeats of the cross-validation process. When I submit a paper, we use 100 times, for example. So it depends on how much time you have to, the more the better, obviously, but don't want to go too much. But for this example, it's going to do 10 repeats of the cross-validation process. So it's going to set around a variable called reps to be 10. And then I'm going to initialize a cv.error vector, which will be the cross-validation error for the 10. So we're going to get 10 things in that vector, 10 repeats altogether. And so now I'm using a different index. So before I use j, I'm going to use I now. So for I, in 1, 2, the number of repeats I do, I repeat this whole cross-validation procedure. And so what I'm going to do is that I get a cross-validation error for one cross-validation loop, put it in the error vector and then repeat this process over and over again, and I get a vector of errors. And then it's nice that you can actually visualize the error process. So if you only had one cross-validation loop, you get a single observation, which you can't really do much with. But if you repeat this process more than once, 2 observations is probably not that good either. So if you, for example, 10 points, you can get a box plot of how the variability associated with the cross-validation error as well. So here, this is for k and n with the best, so I've used the best value of k in this example, so k equals 21. The median cross-validation error is between these 2 points. I don't know what point that is exactly, but you can see here the most we got was 27.5%, and the lowest we got was somewhere below 25%. So if you just do one cross-validation error loop, it's just one error for one particular like setting up the data set, but you want to be able to see if you repeat this process over and over again, how is it performing? And so if you were to have quite a large spread, that means that your model sometimes works on a particular way that the data is spread out. And so really good procedures will have low variability in their cross-validation errors, and they'll be quite low as well. And so the next part is just repeating this process for random forest. So you did one cross-validation procedure for random forest, so you can repeat that 10 times and get a box plot for that. And then you can compare that with the box plot you would get if you did k and n 10 times with the best value of k, and see over 10 repetitions which method maybe consistently does better or consistently does worse. So that's the next task.